Hey, AP Statistics. So, continuing section 9.3, we're going to start by looking at the relationship between two-sided significance tests and confidence intervals. So, the link between two-sided tests and confidence intervals for a population mean allows us to make conclusions directly from a confidence interval. And we kind of did this last chapter where we say if a parameter is something or not it based on whether it's in the confidence interval. So, if a 95% confidence interval for mu does not capture the null value, mu naught, we can reject that mu naught in a two-sided test at the 5% level. So those directly correspond. It doesn't need to be a two-sided. The one-sided test is kind of weird because it ends up being like half that, or depending on how you half the complement. So that's the case there. If the 95% confidence interval does not contain it, then we would reject it at the 5% significance level. If a 95% confidence interval captures the null value, then we should fail to reject in a two-sided test at that 5% level. So the same logic applies to other confidence levels, but only for a two-sided test. So 99% corresponds to a 1% significance level, and so on. Example problem. At the Hawaii Pineapple Company, the mean weight of pineapples harvested from one large field was 31 ounces last year. A different irrigation system was installed in this field after the growing season. Managers wonder if this change will affect the mean weight of future pineapples grown in the field. To find out, they select and weigh a random sample of 50 pineapples from this year's crop. State an appropriate pair of hypotheses for a significance test in this setting. Be sure to define the parameter of interest, and we'll do some other questions after that. But first one, we want to test that mu equals 31 versus mu is not equal to 31. Is it different based on changing the irrigation system, where mu is the true mean weight in ounces of all pineapples grown in the field this year after the change? Part B, check their conditions for performing a test in Part A. So, and the name would be a one sample t-test. The conditions random sample, 10%. Their sample is less than 10% of all the pineapples. And then the large counts, we normal/large counts, we're good. 50 is greater than 30, so that's nice when that's the condition. Part C, a 95% confidence interval for the mean weight of all pineapples grown in the field this year is from 31.25 to 32.61. Based on this interval, what conclusion would you make for a test of the hypothesis of Part A at the 5% significance level? So remember, this was a two-tailed test with mu equals 31, and because that interval does not include 31, it goes from 31.25 and up. That means 31 is not a plausible value. We reject it. We would reject the null hypothesis, and we would have convincing evidence that the mean weight is not 31 this year. And the Part D, can we conclude that the different irrigation system caused it to change in the mean weight of pineapples produced? Explain your answer. So this is actually not related to this chapter, but this is an observational study. So no, this was not a randomized comparative experiment, so we cannot infer causation. It's possible that other things besides the irrigation system changed from last year's growing season. Maybe the weather was different this year, and that's why the pineapples have a different mean weight than last year. So don't jump to cause effect unless you have an experimental design where we keep control other variables here. That may not be the only variable that changed. All right, and then the last thing from this section is power of a test, and power is a weird concept related to the errors. So researchers often perform a significance test in hopes of finding convincing evidence for the alternative hypothesis. So researchers would make a type 2 error if they failed to find convincing evidence for the alternative hypothesis based on the sample data, and if there actually was the alternative hypothesis is true. And then how likely a significance is to avoid a type 2 error, is it called power? So it's how likely we would reject when we should reject. So the power of a test is the probability that the test will find convincing evidence for the alternative when the alternative is actually true. And so we'd like for that to be pretty likely. And so that's something that we want to think about, the power of a test, and how we can increase power. Mainly make it more likely for us to detect a significant result. So let's return to one last time to the company that developed a new deluxe AAA battery that is supposed to last longer than its regular AAA battery. Based on years of experience, the company's regular AAA batteries last for 30 hours of continuous use on average. The company plans to select an SRS of deluxe AAA batteries and use them continuously until they are completely drained. Then it will perform a test at the alpha 0.05 significance level of mu equals 30 versus mu is greater than 30. Looking for significant evidence that it's improved. Where mu is the true mean lifetime in hours of the deluxe AAA batteries, the new batteries are more expensive to produce, so the company would like to be convinced that they really do last longer. The power of the test to detect that mu equals is 31 hours. So these power calculations, a lot of times you have to have an actual mean. So if the mean was actually 31 hours for these deluxe batteries, they calculated the power. There's a 76% chance. And so interpret this value. So 0.762. If the true mean lifetime of the company's deluxe AAA batteries is actually 31, there is a 0.762 probability, or a 76% chance, that the company will find convincing evidence for the alternative hypothesis. So that means that we could get an X bar, right? If the mean of the population is 31, I could get an X bar of 31.5, or it could be a little bit lower. So a 76% of those samples would lead us to reject if we thought about the actual sampling distribution compared to what we would expect, how far an X bar would need to be to cause us to reject. So in the previous example, the probability that we reject the null hypothesis, given that mu really is 31, is 0.762. So then what's the probability that they make a type 2 error? It's just the complement of that. So 1 minus 0.762 is 0.238, and so power is just, it's the complement of a type 2 error. The power of a test to detect a specific alternative parameter value is related to the probability of a type 2 error for that alternative. So power is equal to 1 minus the probability of a type 2 error, and the probability of type 2 error is 1 minus power. You don't need to always call this, but we also sometimes call this beta error. Remember, type 1 error is the same probability as alpha if the null hypothesis is true. That one's pretty simple. Probability of a type 2 error, sometimes they call that beta, and so it'd be 1 minus beta. You might see that somewhere out there, but it's just the complement of a type 2 error. So what can researchers do to increase the probability of making a type 2 error? Decrease the probability of making a type 2 error and increase the power of a test. And so the easiest ways to do this are the power in a significance test to detect an alternative value of the parameter when the null hypothesis is false and the alternative hypothesis is true, based on the sample of size n and significance alpha will be larger when, the best way to do this actually is the sample size is larger. So if we make the sample size larger, what we do is we shrink our expected sampling distribution, and so that brings in how far out we need to get smaller p-values, makes us more likely to reject, especially then also for whatever our actual mean is, we're likely to get things closer to it. So larger samples going to make things better, going to make things more powerful. And then actually the other thing we can do is we can increase the significance level, which is, we're going to make it go from 5% to 10%, for instance. We're going to make ourselves more likely to reject. That might be good. It might make us, our test more sensitive. The problem then is that we might end up getting that alpha levels are type 1 error. It might, has the downside of we might get more false rejections when we shouldn't. So we have to think about the balance between the type 1 error and the type 2 error. But yeah, those are directly related. If one goes up, the other goes down if you adjust that alpha level. Sample size doesn't affect the type 1 error. It just creates a more powerful test. And then the last thing you never really have control over, but if the null and alternative parameter values are further apart, that makes it better. So if the actual mean is 31, our power may not be as high as the actual mean is 36 in that last example. The further apart they are, it's easier for us to tell and get significant results. So example problem here, the researchers in Alzheimer's experiment want to test the drug manufacturer's claim that fewer than 10% of patients who take its new drug for treating Alzheimer's disease will experience nausea. That is, they want to carry out a test of p equals 0.1 versus p less than 0.1, where p is the true proportion of patients like the ones in the study who would experience nausea when taking the new Alzheimer's drug. Earlier we mentioned that the power of the test to detect p equals 0.08 using a random sample of 300 patients and a significance level of 0.05 is 0.29. Determine whether each of the following changes would increase the power of a test and explain your answers. So what if we used an alpha level of 0.01 instead of 0.05? So we're going to need smaller p-value to reject. And so in that case, that's going to decrease our power. So if we use a smaller p-value, if we use 0.01 instead, it's going to be harder to get that significant result. So that's going to, decrease our power. The second example, if the true proportion was 0.06 instead of 0.08, so remember that we were testing that it was less than 10%, so 0.06 is further away. And so that's going to make it more likely to reject. It's easier to detect a bigger difference between the null and alternative parameter value. And then the last one, choose to a sample size of 200 instead of 300. That is going to make it worse, decrease our power. Smaller sample size gives us less information about the true proportion P. All right, and then one last little bit for this chapter, using significance tests wisely. There's some common mistakes. So statistical significance is not the same thing as practical importance. So to help evaluate practical importance, give a confidence interval for the parameter in which you are interested. Confidence intervals are not used as often as they should be, whereas significance tests are perhaps overused. So some people might say, oh, there's a statistically significant difference here, but then when you give the confidence interval, you're like, oh, well, it's only different by so much that's we don't really care about the amount of difference. Even though it's statistically significant, doesn't necessarily mean the difference is practically significant. And so that's one thing to be aware of. The other thing is beware of multiple analysis. So searching data for patterns is certainly legitimate, but performing every conceivable significance test on a data set with many variables until you've obtained statistically significant results is not. This unfortunate practice is known by many names, including data dredging or p-hacking. So if you basically keep doing like, ooh, is this significant? Did we get more 5s than we should have? Or, looking at your data, or is it higher, or is this value different? If you keep doing significance tests, you're going to get a false positive, a type 1 error, where you're going to get a significant result because you just happen to. So be careful about that. In any set of data, you could probably find something weird about it that would only happen less than 5% of the time. Well, yeah, 5% of the time is actually a decent amount. If you do like 100 different ways of testing it, yeah, about 5% of those tests will end up just by chance being that way. So beware of multiple analysis as well.